Okay, let's take a look at some exercises with involving rotational equilibrium. So there's some figures we have here, several figures, and in each case we want to determine this force F that is needed, the magnitude of this force F, the directions given for us obviously, that's needed in order to put the object in, or maintain the object in rotational equilibrium. So rotational equilibrium, remember, is when the sum of the torques around any point is equal to 0. And so it actually tells us, for this problem, we're looking for the sum of the torques about point A, right? Or technically it's not a point A, it is an axis that goes through A, and this axis is perpendicular to the screen here, so into and out of the screen. We'd actually define the positive direction of this axis to be out of the screen and the negative direction to be into the screen. And that's what relates to our positive and negative torques, right? So we take the sum of the torques around any point, and we're going to take the sum of the torques for this one. We're going to take the sum of the torques around point A equals 0 is what we're looking for here. So it looks like we have, these are all perpendicular to the bar, right? The bar is in the x-axis and the force is in the y-axis. It's like we have a coordinate system right here. We have the y going through like this, and we have the x over here. And then what we can do is I think the easiest way to go about this is to just take our torque as force times moment arm. It's a perpendicular force times the moment arm, right? This is actually the magnitude of the torque is just the perpendicular force times the moment arm, and the direction of it. It's actually, the direction is either into the screen or out of the screen, so basically we either have a positive torque or a negative torque, and this counterclockwise, this is actually, if I have something called a counterclockwise rotation, this is actually a positive. It's coming out of the screen. This is a positive. It's like, if you, and where this comes from is something called the right hand rule, right? So if you take your right hand and you put it on top of the screen and you curl your fingers this way, it has to be your right hand, curl your fingers this way, then your thumb points up out of the screen. And if you put your fingers on the screen and you curl them this way, then your thumb would have to point into the screen, which we call negative. So the coordinate system that we use for this is, we'll use a positive x to the right, positive y upwards, and a positive torque is counterclockwise like this, okay? And so we just say, all right, we have the magnitude times the moment arm, and then we determine if that's going to cause a clockwise torque or a counterclockwise torque, and then apply the sign accordingly. That's the most straightforward way to go about this, I think. So we have two torques produced about point A. We have the torque produced by the 50 Newton force, and we have the torque produced by F, right? So if I sum these torques, sum in the torques about point A, and this is going to be, let's take the 50 newtons first. So 50 newtons times, I'll put this in meters, 0.3 meters. So 50 newtons times 0.3 meters. And this is going to produce, if I think about it here, A is stationary. It stays still right here. Doesn't actually move. This point over here moves, right? And the way it's going to move, if I were to push in the direction of F, then this bar is going to rotate clockwise. I could, I guess what you could do is you could like hold one finger at point A over here, and then move your finger on your other hand in the direction of F, and you'd see that if you keep the same distance away, that finger is going to have to rotate around like this. Play around with this a little bit. Take your pencil, actually. You know what you could do, maybe the easiest way to go about this would be to take your pencil, just hold it at some point, roughly A here, and then push on it in this direction. So push on it upwards, and you'll see that it rotates clockwise, right? And so we call a clockwise rotation negative, so there should be a negative in front of here, right? So negative 50 newtons times 0.3 meters. And then plus, because we're summing, I might add a negative, but a plus, F times 10 centimeters, so F times 0.1 meter. And should this be a negative, we actually, if I look at this here, if I were to hold my pencil here, push on the other end, I would see I'm going to have a counterclockwise rotation, so that's positive, right? So it remains positive here. And this equals 0. Because if it's in rotational equilibrium, the sum of the torques around any point, in this case point A, is equal to 0. And so then solving this, we have F, the magnitude of F, is equal to 150 newtons. And the direction is given in the free body diagram here. Quick little thing, and as you play around with summing torques, you'll see this as you experience it more and more. But it ends up just being a quick little ratio of if I have a longer moment arm, this one's a 30 centimeter moment arm, 50 newtons. Then this is a shorter moment arm, so the force needs to be greater, because it's really the force times moment arms have to balance out, right? And so since this moment arm is only 1/3 of this one, this force must be 3 times that one, which is where we get 150 newtons. So after you do sum of torques with lots of problems, you'll probably be able to do this ratio very quickly, actually. All right, let's take a look at another one. So summing the torques about A. The sum of the torques about A. This 50 newtons is going to be clockwise, right? So this is negative 50 newtons times, I could actually leave it as 10 centimeters, but just for standard units, we have 0.1 meters. And then this force F is going to be counterclockwise about A, right? And so then it's going to be plus F times 0.3 meters equals 0. And solving this, we have F is equal to 50/3 of a newton, which is, same thing same relationship we ended up with previously. This moment arm is 1/3 of this one, so this force must be 3 times as much. The 50 newtons, this must be 3 times F, or F is just 1/3 of the 50, right? 3 times the moment arm, 1/3 of the force. I just realized, though, that this exercise actually asks us for another little piece of information as well. It said find F to make it in rotational equilibrium, but then also determine if the object is in translational equilibrium as well. So we want to determine if it's in translational equilibrium. So translational equilibrium, this is one, so it's not translating. It's not accelerating in translational motion, which is just like in the X, Y, Z directions. So in order for translational equilibrium, this is the equilibrium that we've discussed before. We'd have to have sum of forces in X and the sum of forces in Y. And, if we had 3 dimensions, the sum of the forces in the Z would all be equal to 0. So we look at this and we can say, is this, assuming that there are no other forces acting at A, if I sum the forces in the Y direction here for this first one, this is equal to 50 plus F, where F was 150 newtons. And so then this is equal to 200 newtons. So clearly the net force in the Y direction is not 0. It's not in translational equilibrium. Basically what happens here is that it's like, if I were in class and could give a demonstration, I would use a meter stick. But maybe what you can do here, see if I can demonstrate this. Hold your pencil and just push up on the right side with some force F. And you'll notice when you do that, so the only force you have on it is just this force F. When you do that, then it's going to rotate, and it's going to rotate around like this, okay? Now take your left hand and put it on the left side, and also push up with that one so that it doesn't rotate, because we want it in a rotational equilibrium, right? And so by pushing up here, it rotates. By pushing here, it doesn't rotate anymore, but now you're pushing up with both of these, right? So you're pushing up with both your fingers, and now it's going to accelerate upwards. So not in translational equilibrium, but it is in rotational equilibrium. And later on, if I ask, put it in equilibrium, or what's the force for it to be in equilibrium in general, that means both translational equilibrium and rotational equilibrium, if that's possible. But we're just determining what, if it is in translational equilibrium. In order for it to be in translational equilibrium, this would actually have to be fastened here, and there'd have to be a force down like that, right? Okay. So also for B here, the sum of the forces in the y direction, this is 50 plus 50 thirds, which I honestly don't care what that is. I just care that it's not equal to 0. So it's not in translational equilibrium. Okay. All right. Next one. C. Now we have 3 forces. But we do it the same way. Summing the forces about A. And it's, make sure you always put down here what point you're taking the sum of the forces around, or what axis. Then sum of forces about A, I'll just start with the 50 Newton, that's clockwise. The 40 Newton is also clockwise. Both of these are negatives, right? And so negative 50 Newtons times the moment arm here, careful that it's not just 10 centimeters, because it has to be the distance from A, right? So it's the 20 plus another 10, 30 centimeters, right? So we have 0.3 meters minus 40 newtons times 0.2 meters, 20 centimeters for the moment arm for 40 newtons, right? Different moment arms, those forces act at different places. And the force F is positive, causing a counterclockwise rotation, so plus F times 0.1 equals 0. Solving this, we end up with F is equal to 230 newtons. And actually, I can just do this by inspection. I don't need to sum the forces anymore. I just look at this and I say, all of the forces are acting upwards. Then it's not in translational equilibrium either, right? So this one is not in translational equilibrium. And that's by inspection. Okay, next we have 3 forces again, but taking the sum of the moments about A, this 40 Newton force, because it goes right through A, the moment arm is 0, right? And therefore the torque produced is 0. So I'll write it out in here in my equation just for completeness, but you don't have to show it. Quizzes, homework, exams, if you don't want to. So I won't take off if you don't show points. Or show this part right here. So summing the forces about A, we have again 50 newtons is clockwise, so we have negative 50 newtons times the moment arm here is 10 centimeters, 0.1 meters, plus 40 newtons times 0, and then F is positive, right? So plus F times 0.3 meters equals 0, and from this we get F is again equal to 50 thirds of a Newton. It's actually, as far as rotational equilibrium is concerned, it's the same thing as B. It's actually this same one, they just added another force here. Was it like 40 newtons, which doesn't actually have anything to do with the rotational equilibrium. It would have to do with the sum of the forces in the y direction, right? This one, the sum of the forces in the y direction here is going to be 50 plus 40 plus 50 thirds. So it's a greater net force in the y direction. It would accelerate upwards faster in the y direction. But as far as the rotational equilibrium, it doesn't affect it. Okay, then rotational equilibrium about point A, I should say. Then in E, oh, we finally have one that's going downwards here. See how that plays a role. Then summing the forces and the, summing the torques about A. This is, I look at this 50 newtons here, and then I look at the moment arm is 30 centimeters, and then I think about where the direction of the rotation, and you might think, okay, every single time this one was causing a clockwise rotation, right? And so it was negative every single time. But it's more than just where the force is, it's also the direction of the force. So you still have to, you need to analyze each of these individually. Don't just always get caught up in like, oh, every time the force is on the left, it's negative. Don't do that. You have to analyze the direction of the force as well as the position of the force. And so when I come in here and I say, all right, I'm over here, and if I were to push down, it's going to cause it to rotate around counterclockwise. So it's actually a positive, right? So we have a positive here. The 100 newtons, this is going to cause a clockwise. So then this is minus 100 newtons times that moment arm is 15 centimeters. And F is counterclockwise, so plus F times 10 centimeters. And this equals 0. From this, we have F is equal to, it's actually equal to 0 newtons. Which probably, after we've been doing these long enough, we could probably just note this by inspection. I got twice the moment arm for the 50 that I do for the 100, and so then the magnitude of the torque is the same, and they're both on the left side, but their directions of the forces are opposite, so they're actually opposite direction torques. So this being a positive torque, this being a negative torque, and they balance out, so we don't actually need a force F at all for it to be in equilibrium. So that force is 0. But again, let's check the translational equilibrium, and the sum of the forces in the y direction. This is going to be negative 50. And by the way, I'm using the same coordinate system every single one of these. Maybe I should redraw this, but I just do it for the one coordinate system there. So summing the forces in the y direction, we have negative 50 plus 100 plus F, but F was 0. So this is equal to 50 newtons. So this one's not in translational equilibrium either. Not in translational equilibrium. None of these are actually in translational equilibrium. So, so torque, easiest thing, easiest way to go about it. And this sort of, when we're dealing with torque on two-dimensional objects, torque itself is actually 3 dimensions, but that's kind of beyond the scope of this class. We just take, the magnitude of the force times the distance, the perpendicular distance between the force and the axis that we're taking the torque around, and then we just determine if that's going to be clockwise or counterclockwise. And positive is counterclockwise, negative is clockwise.